Hello, yeah. In this video, I want to continue our series on causal analysis using R. Today, I want to show you how to implement Judea Pearl's dual calculus. Okay. So the dual calculus created by Judea Pearl uses three rules to transform causal expressions with interventions called the dual operator into observational terms. Its goal is to identify causal effects from observational data given assumptions encoded in a causal graph. Rule number 1 allows adding or removing observations when certain conditional independencies hold. Rule number 2 is let you exchange actions, interventions with observations under specified graphical conditions. And rule number 3 permits insertion or deletion of actions with specific identifiability criteria met. So the dual calculus is built on a graph model, and there's a lot of the DAG, showing the causal pathways, and it really works for observational data and try to estimate the causal effect of the intervention on the outcome without randomization. Okay. All right, so it's a very sophisticated theoretical system developed by Judea Pearl, and in this video tutorial, we'll just go over a simple example to demonstrate the R package causal effect and how we can use it to implement the dual calculus. Okay. So first, let's do let's load some libraries. We need causal effect, and we need igraph, and we need a mediation because we do want to demonstrate how to do mediational analysis. And then we have the dplyr for do some calculation using data frames. Okay. So first we can load these 4 packages and then use the igraph. I don't think this igraph syntax is necessary here because we loaded the library, so we can use this. So graph forum literal, we want x have a path to z, and z goes to y, and then x goes to y. Okay, so this is a very simple 3 component causal graphs. Okay, and then we can generate our data set, set random seed, sample size 1,000. So in this case, we use 3 binary variable x, y, z, and x is the intervention, and z is the potential confounder or mediator, and then y is the outcome depending on x and z. And put them together as a data frame. This is what it looked like. Okay, so first we do the dual calculus identification expression. So we use the causal dot effect function. We specify outcome y equal to y in the data frame, the x equal to capital letter X in the data frame, and z equal to null, and g equal to g here. Okay, so we put that in the DAG function into this, the DAG we specified into this function, and this will give us a causal effect expression. If we print it out, it looks like this. Okay. So what this means is this is actually the probability of y given dual of x. And this is a kind of a critical concept in Judea Pearl's work. This is the probability of y when we intervene and set x to a specific value rather than just observing x. So it is really different from the traditional conditional probability of y given x. Conditional probability of y after observing x. So here we actually try to mimicking the interventions so S can have different values. And this probability distribution captures the causal effect of X on Y, isolating the impact of actively changing X. Okay, so that's the key concept. And so we printed out this causal effect expression. It's the total sum with regard to Z of the product of conditional probability Y given XZ times probability of Z given X. Okay, so this gave us a way how to calculate this by using observed data. Okay. So next step, we want to use this formula identified by the dual calculus to estimate the average causal effect with backdoor adjustment, adjusting for Z as before. Okay, so we can first calculate the first term called P probability of Y given X and Z. So using the package dplyr. So we do this. So data feed into group by X, Y. So for all the combinations of X and Y, we summarize the mean of Y and save it to P, the probability, and groups equal to drop so that it's become a normal data frame, okay, to get rid of the group structure. And then you want to take a look at this object, it looks like that. Okay, so it's a data frame there. And then we want to calculate P probability of Z given X. So data feed into this pipeline group by X, Y, Z. And then for each combination of X, Y, Z, we summarize the total count in that combination and then return it to a normal data frame. And then we do another grouping by X value. And then we calculate a probability of count divided by total sum of count. And then we do the N group to return it to a normal data frame. This is what it looked like. Okay. So after we calculate these two data frames, now we get the conditional probabilities. So we can calculate estimate underscore 1. So this is the probability of Z given X and times probability of Z given X and let X equal to 1. Okay, so that's using the formula but specify X equal to 1, which we assume to be the intervention. Similarly, we can do this sum, total sum, with regard to all the Z's, but restricted to X equal to 0 is the control groups. Then we have the average causal effect, the ACE, to be the difference of 1 and estimate 1 and estimate 0. And we can print it out. The average causal effect of X on Y, the backdoor, after backdoor adjustment, is 0.0702. All right. So, and so this is a demonstration how we can actually use the formula or the expression identified by the dual calculus to actually calculate the ACE using observed data. Okay. And then we can actually do the causal analysis using the mediation package. So first we can fit the mediator model. So we have a path from X to Z. We fit that. Since both are binomial, binary, we use the logistic regression. Okay, and for the outcome, Y regressed on X and Z, also use the logistic regression. Okay, and then we can conduct the mediation analysis using the mediate function in the mediation package. So the mediate, med fit, and outfit treatment equal to X, mediate equal to Z, bootstrap equal to true, and simulations equal to 1,000. And we can, that takes some time. It's doing non-parametric bootstrap. Okay, now it's done. So if you look at the output, it gives us this table. And It has the estimate and 95% confidence intervals and the p-values. And you can see the ACME is average causal mediation effect, and ADE is the average direct effect. So the ACME is the effect of X on Y through Z. ADE is the effect of X directly on Y. Okay. And then you have the total effect, which is the total sum of all the previous average indirect and direct effects. Okay. And you have proportion mediated, that's the proportion of mediated effect over the total effects, and stratified by groups in the control and treated group. Okay. And then we also have the total averaged ACME and ADE and the proportion of mediated. And you can see if you look at the p-values, we have significant direct effect in both in the control and both in the treatment. So there's no differences in the two groups, but the direct effect is significant, but the total average is also significant. Okay, but the mediated effect, the ACME, is not significant for both groups. So from this mediation analysis, we can conclude there's no mediational effects. Okay, so then we can do a couple more analysis. We can do the causal effect of say Z on Y adjusted for X. And this is the do calculus. Okay, and then we can also plot out the visualization of the DAC. And this is the very simple potential mediation model. Okay. And by the way, I want to mention there also is the sensitivity analysis function, but it also works for continuous variables. So it doesn't work for the data here because our X, Y, and Z are both binary. So if they are continuous, then we can also perform a sensitivity analysis or the causal mediation analysis we performed. Okay, thanks for watching, and please like our video and subscribe to our learning channel. Thank you very much.